Thank you. Good morning. This is a novel experience for me to speak at 9 a.m. on Saturday morning. I assume it's a novel experience for you to listen this early. I appreciate you waking up and climbing the hill. This material is less formal than many of the other talks that you've heard at this workshop. And in concert with that, I'd like to keep it informal, and I encourage you to interrupt me throughout. And if you don't, I may end embarrassingly early. So please do. And this is one of a series of 4 talks that Eric gave the first 2. I'm giving the second 2. And we think of them as a unit. And I want to mention that we're writing a book on this. And part 1 is linkage folding. Part 2 is paper folding. And part 3 is this polyhedra folding and unfolding. So this is part 3 of the book. And the outline of what I'll speak about this morning is 2 parts, roughly equal. The first part will concentrate on what I call reconstruction of convex polyhedra. And this is largely known material, none of it mine, and I'll take you through this. And the second part, folding polygons, should be new to most of you. And this is my work with Eric and our other collaborators. The first half, on the reconstruction of convex polyhedra, I want to touch on 3 topics: Cauchy's rigidity theorem, Alexandrov's theorem, which maybe not all of you know, and Savitov's algorithm, which is fairly recent, and so most of you wouldn't know that. And the second part, on folding polygons, I'll talk about algorithms. I'll show you some examples, and I'll end with, I think, a nice question. And I tried to count. I think I have 8 open problems in the 2 talks, and I think they're very accessible. And it's a relatively new field, so I think you can jump right into this. So let me start with the reconstruction of convex polyhedra. I want to view this as taking some information about a polyhedron and finding those convex polyhedra which satisfy it. For example, the face angles, the edge lengths, the face areas, the face normals, dihedral angles, whether it's inscribed or circumscribed around a sphere. And there are a number of theorems that mix this information and somehow give you a convex polyhedron. You know from Gunther's talk yesterday about Steinitz' theorem, where this depends on the graph information. And many of you know Minkowski's theorem, which starts with the face areas and the face normals and concludes that there's a unique convex polyhedron that realizes given face areas and face normals. This is a pictorial version of it. If you are given normals to faces whose length is proportional to the area of the faces, there is a unique polyhedron that realizes that. And Cauchy's theorem can be viewed in this light as taking information about the structure of the face, how the face is glued together, the face angles, the edge lengths, and how they're all put together, so the graph information. So here's one statement. It's often called Cauchy's rigidity theorem. If 2 closed convex polyhedra are combinatorially equivalent with corresponding faces congruent, then the polyhedra are congruent. And in particular, the dihedral angles at each edge are the same. Now let me say something about this word rigidity. This is how I've always heard it, but this is not exactly the same sense of rigidity as in Eric's talk, where it's closer to what is called global rigidity, which is really a unique realization. So it's conceivable that a convex polyhedron would be rigid and that you cannot flex it, but there could be several realizations of it. But this is even stronger. There's just one realization given all of this information. So of course it's rigid, but that's the sense in which the rigidity theorem is used. Now I want to say that it definitely depends on convexity here, because here is an example of 2 incongruent polyhedra with the exact same facial structure, same face angles, put together the same way. And of course this can be repeated. So you need convexity in order to get this uniqueness result. Now what I'd like to do is take you through a quick outline of the proof. Many of you have seen this, especially if you've read proofs from the book. Proofs from the book. And some of this exposition here is taken from Gunter's book. It's a very pretty proof, and I will only just sketch the main idea so you get the sense of how you could prove Cauchy's rigidity theorem. One of the key concepts is to put a ball around a vertex and cut the polyhedron into these spherical polygons and reason with those. So here's a particular vertex. You cut it with a small sphere, and this is another view. You get this spherical polygon. And you can see that the dihedral angles here correspond to the internal angles of the spherical polygon. And the edge lengths of the spherical polygon, these, correspond to the face angle of the corresponding face incident to the vertex. So the dihedral angles and the face angles are evident in this picture. So let me go back to this. So this is what I'd like to prove, that you have two closed convex polyhedra. They're combinatorially equivalent, and you'd like to show that they're congruent. And the proof is by contradiction. Suppose that you have two closed convex polyhedra that are combinatorially equivalent with all this information the same, and yet they are not congruent. So if they're not congruent, they have to differ someplace. There has to be some different dihedral angles, and we'll concentrate at some. We now imagine that we're taking the two polyhedra and doing the spherical polygon around some vertex where they do differ geometrically, where the dihedral angles differ. And now we're going to compare these two spherical polygons, which are called Q and Q prime, and mark the vertices, which, remember, the interior angles of the spherical polygon correspond to dihedral angles. Mark those vertices as plus, minus, or 0 if they're larger in Q than in Q prime, or smaller, or exactly the same. And around these two spherical polygons that we're assuming for contradiction, there has to be some pluses or minuses, not all zeros, because they do, in fact, differ. And one of the key lemmas in Cauchy's proof is that the total number of alternations in sign, as you run around, you see plus, 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 minus, that's an alternation, minus, minus, 0, plus, that's an alteration. The total number has to be at least 4. And I think you can see immediately it has to be even because it's a cycle. You can't have an odd number of sign changes. So if it's to be at least 4, you have to rule out it being 0 or 2. And the argument for 0 is a little easier to see than 2. So here I imagine this is the spherical polygon for Q, and I've labeled 0, plus, 0, etc. So this is the case where there are 0 sign alterations. They're all pluses, no minuses. This means that in Q, it's all the dihedral angles open with respect to Q prime. Now, because the face angles are the same by assumption in the two polyhedra, the arc lengths of the spherical polygon are all the same. But in fact, if you open up these dihedral angles, you must stretch one edge, E to E prime. This is called Cauchy's arm lemma sometimes, and you may know it has a somewhat speckled history. His original proof was incorrect, and it was not corrected until in the 1930s, maybe, by Steinitz. So it's a fairly tricky argument. But anyhow, this gives a contradiction. You cannot have 0 sign alternations because it would have to get bigger. Let's turn to 2 sign alternations. If you have 2 sign alternations like this, you have a number of minuses and zeros, and then a number of pluses and zeros. You could find some chord across the spherical polygon which separates the pluses from the minuses. And now concentrate on the plus side here. And again, you use Cauchy's arm opening lemma to conclude that this chord that I drew, S, has to get longer to S prime. And now I want to switch viewpoints, and I don't have another figure for this, and look at Q prime versus Q rather than Q versus Q prime, where all the pluses become minuses and the minuses become pluses. So all these minuses then represent a plus from Q prime's point of view. And from that point of view, S prime must grow to S, and you get a contradiction. So you conclude that S must grow to S prime, and by the other point of view, S prime must grow to S, and you can't have both simultaneously, so there's a contradiction. So you cannot have 0 sign alternations. You cannot have 2 sign alternations, so you must have at least 4 around every boundary. And now the last step in the proof is that this large number of sign alterations is incompatible with Euler's theorem. And you count the sign alternations in 2 different ways on the surface of the polyhedron, and you count the total number of sign alterations. You know it has to be more than 4 times the number of vertices, and I will not show you this. It's not completely evident, but this leads to a contradiction to Euler's theorem, and so this can't happen. So that's the end of that proof.
So why is it 4 times the number of vertices? Because you started with a vertex where it looked different. So it's 4 times the number of vertices that are different.
Yeah, there's another vertex on the edge. So let's see. That's a good question, though. I'm not seeing it at the moment.
Sorry.
So what comes out of Euler's equations is that there must be a vertex where there is a change, but there's less than 4 changes.
Okay.
Yes,
I mean, you have to. I mean, you said that there can't be less than 4 alternations, but of course there can be 0.
There can be 0. That's what
changes,
Frank is asking.
Which means you look at only the part of the graph of the.
Oh, I see. You only look.
Something changes, and then it works out.
I should read the proofs from the book again. Thank you.
You know that writing is always gets you even closer to the reading.
So I mentioned that you need convexity. You also need closure, because this is certainly not true for polyhedra that are not closed. This is just the top of an octahedron made of polydrons, and it flexes. That's actually better than the model here. So you get a degree of freedom here, and you can kind of see the sign alternations here, incidentally. And this leads me to talk about flexing polyhedra. Many of you know that for years it was unknown after Cauchy's proof, and thought perhaps true, that all polyhedra are rigid in this same sense, and until Bob Conley found a flexible non-convex polyhedron, necessarily non-convex polyhedron, and it's a very intricate construction. I don't have a picture of Conley's, but it depends on something called Bricard's octahedron, which I have here, which is a very nice linkage structure. This is made out of straws and string, which flexes in this nice way, but it quite self-intersects, so it's not a real polyhedron. And Bob Conley managed to take the essence of Bricard's polyhedron and avoid the self-intersection. And it was a real achievement, and very subtle. It only flexes a little bit. And since then, it has been improved in the sense that this example by Stefan has only 14 triangles and 9 vertices. And this flexes. And it's not evident that this flexes either. And even when you see it flex, it's not evident that it's flexing. But there you go. This is Stefan's page. I don't know if that's convincing or not, but it's moving a little bit. It's just 2 frames, but I don't have a good movie of this. But yes, I've built paper models, and it's so subtle that you cannot tell whether you've taped it incorrectly. For example, I have a tetrahedron here that I can flex. You know, once you make it out of paper, these things flex so little that you can't. You'd have to make it out of very stiff cardboard. And
yeah, well, because I've made paper models that are actually pretty stiff.
Uh-huh.
But it's not just taping the edges either.
Right.
So
You use cardstock.
glue them. And
Yeah.
cardstock and all
I haven't made a really good one of this. You're right. I should probably do that. And this leads me to the Bellows conjecture, which will get me to the heart of Savitov's algorithm. So that's where I'm going here. After the flexing polyhedra were discovered, it was noticed quite quickly, I think by Conley and others, that the volume doesn't change. And this was put in a nice way by Mackenzie, that polyhedra can bend, but they cannot breathe. So you could not, the conjecture was that you could not make a bellows to pump air out of a flexing polyhedron, because in fact, even if you put a little hole in it, no air would come out or go in because the volume doesn't change. And this was settled rather recently by Conley, Sabatoff, and Waltz. And I'm not going to describe too much about this, but there is a key part of it that is relevant. You're all familiar with Heron's formula for the area of a triangle, which is written this way. And one way to view this is if I give you the 3 lengths of a triangle, you can compute the area, where S is the sum of the lengths, I guess. And less commonly known is Francesca's formula for the volume of a tetrahedron given its 6 lengths. It's a rather complex equation. It's discovered in the Middle Ages sometime. I'm not sure the exact year, 1500, something like that. And Sabatoff recently, in the 90s, developed a vast and beautiful generalization of this, and that is that a volume of a polyhedron is satisfies a polynomial in the edge lengths only.
The power of the volume, is it?
A power of the volume, yes. A large power of the volume. And
But it's algebraic.
Isn't it the root of a polynomial?
right, the volume satisfies a polynomial. It's a root of this polynomial. So I'm going to show you in a moment how Sabatoff uses this. Well, it's used, it was a key step in the Bellows conjecture, but it's also used in what I'm calling Sabatoff's algorithm. So let me come back to this.
So what's the resolution of the Bellows conjecture?
Indeed, the volume is constant. You cannot make a bellows out of a polyhedron.
Only out of leather.
Pardon me?
Only out of leather.
Only out of leather, yes. Paper. So let me hold that for a minute and turn to Alexandrov's theorem, which is very much related to Cauchy's rigidity theorem, and perhaps less well known, but more important for what I'm doing here. And the various versions of this, I don't find these all this clear. This is from Alexandrov's book on convex polyhedra. For every convex polyhedral metric, there exists a unique polyhedron up to translation or translation with a symmetry, realizing this metric. And let me give you another version, which is a little clearer for my purposes, from Pogorelov, who was a student of Alexandrov and continued a lot of his work. And this is from Pogorelov's book. I forget the title at the moment. Any convex polyhedral metric, not intrinsic geometry. No, it's the yeah. What was the name?
Intrinsic geometry of surfaces?
Yes, I think that's the book. Any convex polyhedral metric given on a manifold homeomorphic to a sphere is realizable as a closed convex polyhedron. And this is important for me, possibly degenerating into a doubly covered plane polygon. So a doubly, I think you know what that would mean. You have a convex polygon, you glue 2 copies right on top of each other. So we're going to call that a polyhedron. I need that because it comes out of Alexandrov's theorem. The manifold has to be homeomorphic to a sphere. So this is a key part of what we're doing, and I want to rephrase this. This is largely my own rephrasing, but I think it's in the spirit of Alexandrov. Because a lot of his proof techniques involve this, what he called gluing. So I'm calling this Alexandrov gluing. Imagine you have a set of polygons. You're going to glue them together in the following way. You have to use up the perimeter of all the polygons by matching point to point the boundaries. You leave no gaps. You have no paper overlap. So this is different from what Eric was talking about, wrapping polyhedra. We're not going to do that. Everything has to merge. You can glue several points together. That's fine. But at most, 2 pi paper at any point can be glued together. And this is a very natural restriction, because if you glue more than 2 pi, you can't get convexity. So you want 2 pi at most. And you want it homeomorphic to a sphere. And Alexandrov's theorem can be interpreted as if you have these conditions satisfied, then they are realized by a unique convex polyhedron. And I'm mainly interested in the case of one polygon. We're going to take one polygon, glue its boundary to itself in this form, and it must yield a unique convex polyhedron. So here's an example of what I mean by the gluing, and I'm going to return to this again. You take this piece of perimeter, you glue it to this piece of perimeter. You take this piece of perimeter, you glue it to this piece of perimeter. You take this vertex and that vertex, and you glue them all together. And I think you probably know what you get. You get a cube. And you can't get anything else. Once you do this, and for example, when you glue these three purple vertices together, you glue 90, 90, 90, and you're less than 360. So that's legal. If I tried to glue 5 of these 90-degree things together, that would be illegal. Or if I glued this point to this point, that's illegal because it violates the sum of 2 pi. I mean, not illegal. It's not an Alexandrov gluing. So let me distinguish very crudely the difference between Cauchy's theorem and Alexandrov's theorem. In some sense, Alexandrov's theorem is a considerable strengthening of Cauchy's rigidity. Cauchy established uniqueness, but Alexandrov's theorem establishes the existence as well as uniqueness, and the existence is the hard part. And also a second difference is that in Cauchy's theorem, given, so to speak, are the faces and the edges, the face angles, all the edge lengths, and the facial structure, the combinatorial structure, is known. It's part of the input, so to speak, to Cauchy's theorem. With Alexandrov, the gluing of this polygon to its boundary is unrelated to the final edges of the polyhedron. So in fact, you don't know where they are. But they're there someplace, and they're completely uniquely determined.
So you could glue 2 edges of the polygon and it would form a flat?
It could be flat, yes. And I'm going to show you some examples of that.
One of the faces you start out with could be forced to bend.
And faces you start out with, a flat face could be forced to bend, yes. And I'll come to some examples. This slide I don't want to go through too carefully because, in fact, I don't understand all these results here. But I just want to show you there's a long history of many prominent mathematicians working on these uniqueness and rigidity questions for different surfaces. Starting with Cauchy, Alexandrov, Minding proved the sphere is rigid. I didn't figure out exactly what sense that means, rigid. The sphere is...
Round sphere.
Pardon me?
The round sphere.
I think so, yeah. I did not look up all these. The sphere is unique given its metric. Closed regular surfaces are rigid. Uniqueness of these in certain classes and a whole series of other things. And as far as I know, the end point of this is Pogarelev's theorem that if you have 2 isometric closed convex surfaces, then they are congruent, which is a very natural analog to Cauchy's rigidity, except it's just closed convex surfaces. And I do not know precisely what conditions he puts on here, but they're very limited. So the conditions were eventually removed. So what I'd like to do is just give you a hint of the, how Alexandrov proved the uniqueness, the existence of a polyhedron that satisfies that, in my terminology, if you have an Alexandrov group, there must be a convex polyhedron. And it's induction on the number of vertices of the metric, and from a realization of n minus 1 vertex metrics, you move to an n vertex metrics by continuous deformation of metrics, which you track the whole way along by polyhedral realizations until you end up with a realization of n vertices. And here's the center of the proof. You take this polyhedron already realized with n minus 1 vertices, and you want to move it to n. You find 2 vertices whose curvature is less than pi together. And by curvature here, I'll need this later on, the curvature is the angle deficit at a vertex. So you take 2 pi minus the sum of the incident face angles, and if this is 0, it's flat. If it's very if the sum of the angles is near 0, you get a very sharp vertex that's high curvature. Negative curvature would be you have too much paper to be convex. So there are two vertices somewhere on the surface that have curvature less than sum of curvature less than pi. I'll just ask you to believe that. You connect them by a shortest path gamma. You cut along this shortest path gamma, and you suture in a doubly covered triangle, which does not change the total curvature, but it eliminates the curvature at one of the vertices, and then you adjust the shape of the triangle until the other one disappears, and you've reduced the size, and then you apply induction. So I'm going to show you just very quickly what this idea is. So I imagine these are the 2 points on my surface, and this has less than pi. I think I said the sum is less than pi. Each is less than pi. So this is 240 degrees, say, and this is 300 degrees. And this, you put in a little triangle, very small, and you kind of glue it into the surface, and you arrange so that on the front side there's 60 degrees, on the back side there's 60 degrees, and it adds up with this to be 360, and that eliminates this vertex. And now you morph the triangle until you also eliminate this vertex with 30 plus 30 to be 60. And then you have eliminated the A and B vertices, and you've introduced this new vertex C. So you've taken 2 vertices out and replaced it by 1, and you're now down in the situation where you can apply induction. Now, all along, he has to get polyhedral metrics and realize them, and there's quite a bit of argument here that I'm not going through at all. Now, let me mention one acute application of this to something called deforms, which I hope no one has ever heard of. This is a smooth, you take 2 smooth closed convex curves of the same perimeter and glue them together along their perimeter. And this is called a deform. And here's an example here. There's one. There are these beautiful objects. You just cut out of paper any 2 closed convex curves that have the same perimeter, and then just take the perimeter anywhere and glue it to itself all around. And you get these elegant shapes. And this idea comes from this book, Computational Line Geometry, a wonderful book by Potman and Wallner. And this is their drawing of one deform. And they asked in this book 2 questions about deforms. Apparently this comes from some architect who is making these shapes, and they just look beautiful. And you can always do it. And they asked, when is a deform the convex hull of a space curve? So this, you can see that there's this space curve curling around, and this thing looks like the convex hull of that curve. And it also doesn't have any creases. It's just smooth. There are no creases at all.
So you make it out of paper, so they're always ruled. The membrane's flat.
It's a ruled surface here, yep, and ruled this way. Actually, you can see it more clearly on their drawing than on ours. But this is flat up here, perhaps. So you can have flat parts, but it's definitely ruled. And I chose an example that's very much like theirs, but it's quite interesting if you, say, get a nice long ellipse. They just have to have the same perimeter. So you could glue this to this. And it's not evident what you get, but you get something. And so these are the 2 questions. It's uniquely determined, and Eric and I were able to prove using Alexandrov's theorem and Pogoryev's extensions of it to smooth cases that you always get the result is the convex hull of a space curve, and it's always free of creases. And it's uniquely determined. I'm not going to show you any of that. I just wanted to mention as something of an application of this. Okay, let me now turn to Savitov's algorithm. And what Savitov's algorithm does is it takes the edge lengths, let's say, of a triangulated convex polyhedron, and it computes the vertex coordinates. So it's taking those edge lengths and finding the vertex coordinates. And if it's triangulated, then if you take the edge lengths, you also know the angles. And by Cauchy's theorem, there's a unique one. And up until Savitov's algorithm, there was no way to find the unique one. So this algorithm does find the unique polyhedron realized by the input to Cauchy's rigidity theorem, so to speak, and in time exponential in the number of vertices. So here's Savitov's volume polynomial. V is the volume of a polyhedron, and L is a vector of edge lengths, and N is, I think it's the number of vertices. I may be wrong on that, but it's certainly linearly related to the number of vertices. So I mentioned Francesca's formula for the tetrahedron, and it can be written as this, that the volume squared plus some polynomial in the 6 edge lengths equals 0. And this polynomial in the edge lengths looks something like this. You have squares of the lengths multiplied in triples, and you have some plus or minus in front of it. And so you write this out. It's quite a formidable formula, but it is a polynomial in the square of the volume, and the power goes up. And he proved that the volume of the polyhedron is a root of this polynomial. Now let me give you some intuition of, and this is not restricted to convex, so this is arbitrary polyhedron. Let me give you some intuition of why the power has to be large. I'm sorry, n is not the number of vertices. We'll see. I'm using n in 2 different ways. Here n is more the number of vertices. Imagine you have a polyhedron. Make this into a polyhedron somehow, and then do the same trick I did with the cube with a house on top, where you pop it in and out, and make all these slightly different sizes. Then you get 2 to the n different volumes here, and they're all from the same edge lengths. So you must have an exponential number of roots of this polynomial just to capture this. Now, a key to Savitov's algorithm is that his volume polynomial works on things larger than polyhedra. He calls them generalized polyhedra, which, and here's his definition from his paper: any simplicial 2-complex homeomorphic to an orientable manifold mapped to R3 by continuous functions linear in each simplex. This is more broad than I need. The most important thing I want to mention here is it need not be embedded, so the surface can self-intersect. So he generalized the volume polynomial to include self-intersecting polyhedral manifolds and defined it appropriately. And this is key to his algorithm, because during the process it will self-intersect, but still the volume would be a root of this polynomial. So here's a crude attempt at the proof. You take an edge E on the surface of your polyhedron, your imagined polyhedron that you're trying to figure out, and it has 2 incident faces. You know this because that's the input to what you're doing. And those faces determine some diagonal D, which is perhaps deeply interior to the polyhedron, and you have no idea what this is because that's not part of your input. And you're trying to find D. So you pluck off this little tetrahedron that I just showed you, and now you write the volume of the original polyhedron P as the reduced polyhedron P prime, and the volume of this tetrahedron, which will either be plus or minus, depending on whether that little thing I showed you before is inside or outside the polyhedron. So you have to think of a non-convex situation. And after many steps of algebraic legerdemain, he ends up with a polynomial equal to 0, whose unknowns are the edge length vector L, the volume of the original polyhedron, and this unknown diagonal D. And these unknowns, well, the the variables in the polynomial, the edge lengths are all given to you, so they're not unknown. The volume is in some sense known from the volume polynomial, or at least you have a finite number of candidates because it's the roots of the volume polynomial given the edge lengths. So really, there's only one unknown. It's this d. So you don't know what the volume is because you have these exponential number of possibilities, but you try all of them. And then you get zillions of roots. So now you have this exponential number of polynomial equations, each which has an exponential number of solutions in D, and you try all those. And that gives you lots of candidates for the dihedral angle that you don't know. And you do this for all edges. And then you check this vast set of dihedral angles, and you see which one is right, which one gives you the unique convex polyhedron specified by Cauchy's theorem. So this leads to the open problem, which I wanted to end part one with, is it is quite an open problem, and I think very interesting, to find some algorithm, either polynomial time, which would be very nice, or even a numerical approximation procedure that takes as input the combinatorial structure and edge lengths of a triangulated convex polyhedron and outputs the coordinates of its vertices. I would very much like to do this. I can only do it up to octahedra right now. And Savitov's algorithm is of no help, even for an octahedron. OK, so now I'm going to go into the second part. This is, yeah, Boris.
Question. In the sense of numerical approximation, isn't there the spring model?
There is the spring model, and I have actually implemented this, and it doesn't seem to work too well. I can't even do an octahedron with the spring model. It may be that experts in numerical analysis would not find this difficult, but I mean, it's theoretically solvable, but in practical cases, to reconstruct, say, an icosahedron from its edge lengths, it's just hopeless at this point. So. Yes, and I will show you this. Yes, I'll show you this. I'm trying to think, is it this morning or this afternoon? But I'll reach that. I'll show you how I actually do it. And you'll see it has nothing to do with anything I just discussed. OK, so let me go to this outline. This is a new material. I'm going to talk about folding single polygons, for which Alexandrov's theorem is very relevant because it gives you local conditions. And if you satisfy those local conditions, you know there must exist a unique polyhedron that realizes them. Although, as you now see, we have no way of finding that unique polyhedron, but it's there. And I want to show you some algorithms we have for checking for Alexandrov's gluing. And then I'm going to take you through two examples and end with a nice, intriguing open question.
Is being homeomorphic to a sphere a local condition?
No, I'm sorry. That's not a local condition, but it's easy to check. Okay. I shouldn't have said that. The key thing is that just gluing less than 2 pi at each vertex is the local condition. You're right. Certainly, homeomorphic to sphere is global.
But if you know the deficits at each vertex, you know the Euler characteristics of the resulting surface.
Yes.
So that gives you.
Okay, that's.
In fact, actually, the Gauss-Bonnet theorem in discrete form is the Euler characteristic with deficits.
Yes. Okay. So you can just quickly, yes.
Was the problem when you tried to use the string model, or the spring thing, was that like ill-conditioned matrices?
Yes, and I'm afraid I know very little about that. But there's a clear. I just used gradient descent, but you have barriers. It has to be convex. So constantly, you can imagine you build an icosahedron out of springs, and it's all flat, you know, and then all the springs are the wrong length, and then you want them to go to the right length. Things pop in and out, you know, they become non-convex. So that represents a barrier. So it's actually a search in the, you have to use barrier methods, and then they're tricky. You bounce off the barrier, you have to go slightly non-convex. I couldn't manage it. I don't know how hard it is for those who would really know that area. So I want to talk about folding polygons to convex polyhedra, and the first question is just a decision question. If I give you a polygon, can you decide whether or not it folds to some convex polyhedron? And this one obviously folds to a cube. This is less clear, perhaps. Can you see whether that folds to a cube? No, it doesn't fold to a cube, but it folds to something. Then that's not obvious. But because I'm going to skip the actual construction of the shape, all I need to answer is whether or not it has an Alexandrov gluing, and then I know it folds to a unique polyhedron. Let me first show you that not all polygons are foldable in the sense of folding to a convex polyhedron. So I'm using foldability in a very special sense. So I have to glue up this perimeter. I want to satisfy Alexandrov's conditions. One way to glue up this perimeter is to glue A to C, and that won't work because that puts more than 2 pi right there. So that's illegal. So you can't zip this up. You've got to stuff something in there, and there's nothing to stuff in there that's small enough, so you cannot fold this up into a convex polyhedron. And in fact, under some very crude assumptions of what it means to be a random polygon, almost no polygons can fold. So it's rare, although it's actually common in that every convex polyhedron folds to infinitely many every convex polygon folds to infinitely many convex polyhedra. Here's a simple proof. Take a point x, go halfway around the perimeter, mark y, glue xy to yx. And how much angle am I putting here? Well, it's just pi. I have a convex angle glued someplace in here that's less than 2 pi. It satisfies Alexandrov's conditions. So this is a polyhedron, that gluing. And if I just take another x, I get another polyhedron. Maybe another one, maybe the same one, I don't know. So it folds up into an infinite number. Yes?
It cannot be the same one because you moved the vertex.
Well, it could be a square, and
It has to be a vertex.
there could be symmetries in the, yeah. But in fact, this is something of an aside, but we have a proof in one of our papers that there's a continuum of incongruent polyhedra here, but that was, I do not have a nice proof of that, partly because we have no way to construct the polyhedra. So we're missing this piece of getting it into 3D. So let me first restrict attention to what we call edge-to-edge gluings, where you take an entire edge of one polygon, of the polygon, and glue it to an entire edge of itself. And Anna Lubio and I started this in 1996, and we started with the Latin cross unfolding of the cube, which I have here, this shape, and we wrote a program to explore and find the Alexandrov gluings, and we tested it on the cube because we knew what the answer would be. We tested it on this shape, and our code gave us 5 different outputs, and we tried to debug it, and then we realized that they're all legal, actually. These are the 5 shapes that you can get by folding up a Latin cross and gluing edge to edge. And so now this answers some of the earlier questions. So you can have, this is a corner of the Latin cross, a corner meeting the interior of an edge, and it's, of course, 2 pi here, so it's entirely flat. There are creases here that don't come from the original unfolding. It's a somewhat tricky thing.
So what exactly is the problem?
Okay. This is just this shape, fold it up so that you always glue whole edges to whole edges.
So whole edge does not mean a whole straight segment of your initial boundary. It means what you've declared with an edge.
Yes. Okay. Let's see. Okay, here I have an animation. This takes a few seconds to get the cursor. 10 seconds to load. Meantime, I have these here. So here's a typical example. I have it all pre-creased, and you start to fold it up. And you get, in this case, a tetrahedron. Here, you can see it better here. This is a video we made, largely made by Eric Demain when he was a graduate student at University of Waterloo, and has a very nice musical background, which we were not able to get here today. And underneath, that's Alexandrov's great book with the theorem that we're using here. So that's flat. Now we recrease it. That's a no, that's a pentahedron. So there's a quadrilateral face there. This is the tetrahedron. This is the most surprising one to me. I lost count. Was that it? I think so. Right. Okay. So now let me talk about how the algorithm works to list all the Alexandrov gluings for a given polygon. I'll illustrate the idea with this simple pentagon here. We represent the gluings by what we call a gluing tree. So this tree is a representation of one way to glue this to itself. So imagine you, let me walk over here. If you glue E3 to E4, then V4 becomes a kind of a leaf of the tree. So this is the gluing of E3 to E4, and V4 is up there. And you take E5 and you glue it to itself by creasing it in the middle here and pulling it over so V5 matches V1, etc., and you keep going around. So this is, if you look at this, if you crease an edge in the middle, that's okay according to Alexandrov's theorem. And if you add up all these, they are less than 2 pi. And so you get this combinatorial object. We call it a gluing tree. Here I've redrawn it, and I've drawn the curvatures in units of pi. So here, the curvature, this is just the crease of an edge here. So the total angle here is pi. 2 pi minus pi is pi. That's a curvature of 1. 1, 1, 2/3, 1/3 adds up to 4 pi, which is the Gauss-Bonnet theorem. So we must always have 4 pi of total curvature here. So this is the object we use. It's folding in 3 dimensions. As usual, it's not at all easy for me to see how to go from here to here. But this gluing of E3 to E4, maybe we should concentrate on that. That's this thing, and V4 is way up there. And then down here, you have all this pulling together of all these vertices, and it makes this unique polyhedron. Unfortunately, there can be polygons which fold to an exponential number of different have an exponential number of different gluing trees. And this is an example where you can stuff many of these spikes that are labeled alpha into many of the reflex vertices labeled beta in lots of different ways. And these are the gluing trees. Some of the this is one generic gluing tree. This is where you start to glue various things together in different ways, and there are an exponential number of them. Eric and Marty Demain actually made made this for the simplest case and built all of them. And so they really are there. So this means that any algorithm that lists all the Alexandrov gluings would take exponential time because there can be exponential number of results. But they're the general algorithm. Oh, so I'm switching now. We extended this work to remove the edge-to-edge assumption and just stick to any Alexandrov gluing. And Anna Lubiu and independently Koshi Harada in Japan implemented this algorithm that would list all the Alexandrov's gluings. And of course, it's exponential time because it has to list them all, and there can be an exponential number. But I believe even if there are not an exponential number in this case, it still takes exponential time. And it has a dynamic programming flavor.
Can it be polynomial in the output?
I think it should be. I think, in fact, the whole thing could be polynomial. That's one of the open problems. I don't think to decide whether or not it can be done at all. So,
Even if it's pretty
right, even here, not sure. Yes?
I'm missing something. If you can keep folding in the middle to get those spikes, is it obvious that you can't keep doing it and get an infinitely many?
Well, there are definitely examples where you can get an infinite number. For example, just a convex polygon, you can get an infinite number. But here, the constraints of the reflex vertices eliminate the possibility of this sliding that is necessary to get the infinite number. But I don't have a general theory that will tell me whether or not there's an infinite number or a finite number. That's another open problem here. We don't understand it that well. And so here, even this is open. I think this is a nice problem. Given a polygon P, determine just yes or no if it can be folded into a polyhedron. And I worked quite hard on this without succeeding. I think it should be polynomial time and not exponential. I don't think you have to go through the exponential. But now let me turn to two case studies. The Latin cross and the square. And in some sense, these are the only two that we've studied fully. And they represent two ends of the spectrum, as you'll see in a second. So for the Latin cross, if you restrict edge to edge, you get the 5 that I showed you. If you don't restrict, there are 85 distinct gluings. And this is the beginning of a long list of some of the 85 distinct gluings. And Anna's output and Hiroshi's output agreed 1-to-1 on this, which is quite nice. And I reconstructed the shapes by ad hoc techniques that I'll mention in a moment. And it turns out that out of all of these, there are 23 incongruent polyhedra out of these 85 foldings. And here they are, all stretched out. This is supposed to be a unit square on top of the cube over there. And this is the work of quite a number of people, a lot of my students folding all year. And I'll show you, just take you through the variety. So all of these come from folding this in different ways. You get the cube. You get these two flat shapes. You get 7 tetrahedra here. No regular tetrahedron in here. You get a few pentahedra with quadrilateral faces, flat faces. You get some hexahedra, 4 hexahedra, and you get 6 octahedra. And that constitutes all 23 of them. And here I have a display in a kind of whimsical display.
There's no polyhedral structure here. You're just
No. This was just supposed to be art. It wasn't completely successful. So let me mention the ad hoc reconstruction techniques. So given the 6 edge lengths of a tetrahedron, it's determined. And here's actually how I do it. If you plop down one triangle on the plane and you kind of fold up the other 3, and of course they must, the track of the vertex is this circular arc, and they all meet at the apex. And if you look directly from above, you can see that you get these intersection of of perpendiculars here. And I use that to compute this and find the height. So that's fairly straightforward, although a few numerical issues there. For hexahedra, you can see that these hexahedra are all gluings of two tetrahedra, one base to base. So that's how we do that, use the two tetrahedra, so that's also nicely determined. And it's only with the octahedron that we start to get into the Sabitov issues. The octahedra, we can view it as two hexahedra, which I can reconstruct exactly, which are glued together along an unknown internal diagonal of length d that we don't know. So that's one variable, and using Sabitov's volume polynomial, we could find an equation for this. I think it's either degree 16 or 32, or maybe 64, not quite sure. But anyhow, it's out of range. So we do a numerical solution to adjust the length of this, watch the dihedral angle change, match the two dihedral angles until it glues together. And that's how we do the octahedra. And to go beyond that would be hard. And I want to now mention the completely different view of foldings of a square. This is a convex polygon, so there are an infinite number of polyhedra. And one interesting thing is the space of all these polyhedra is connected. Let me show you something about the why it's infinite. Again, if you start with just creasing the square and making a right triangle, you can alter the creases slightly, and kind of morph to a situation where you get a tetrahedron. And in between, those are all legal polyhedra. And we've completely classified these. I think I won't take you through this, but you see there are pentahedra, hexahedra, octahedra, 4 flat shapes. Let me show you those. So one is this, I just showed you. Here's another flat shape, a rectangle. Maybe this is a little bit more difficult, a square. You curl in the, and then some of you may know this as an old puzzle. There's a nice pentagon here where you fold in 2 flaps and fold up the bottom. And here's like the whole world of all of these. And I have a dynamic web page. I hope I can get it up. So this is all the shapes that you can realize from a single square piece of paper. And they're connected into 3 rings. Here are some of the flat shapes. Here's the square here. Here's the rectangle. There's the pentagon. And topologically, they fall into these rings. So this is the one I was just showing. No, that's not the one I was showing you. But anyhow, see this.
So there's one parameter family you get when you just...
Right. So these rings are 1 parameter families here. Let me show you.
And is the big ring the ring you described before, where you glue to antipodal points on the perimeter?
No, it's more complicated. Let's see if, for example, this shape here is made from this. Let's see. Is that? Yeah. Yes, you're right, John. Yes. Okay, that one is. I think I have it right here, and it's slightly damaged from the flight over, but it has just 2 crease points at the end. The orange is the perimeter, and it's this snaky path, but it's just glued to itself. So this is an exact creasing there.
Those are the ones where the tree has no branching.
Right. So these are the gluing trees, and it's just a path here. And then you get different paths. And I have, this is a kind of intricate, I have, examples of all these things here. But let's see if I can show you. This is the whole set of them. Now I'm running around the rings, and earlier in the summer I knew where that was on these rings, but right now I'm not sure I do. But anyhow, we run around the rings, and there's a continuous deformation, and the whole whole space is connected. So now we are, and occasionally you'll see the diagonal, there's the rectangle flipping, so that's where we merge here and go into another ring. And now you get back to a flat piece.
We're not asking if you can concrete. You can reassemble it into
Oh, oh, that enhances its status quite a bit.
so it's in a way it's a Hilbert problem.
Thank you very much.
Questions?
Yes.
Do I understand you correctly that there is no constructive way to construct a polyhedron from Alexandrov data?
There is no, well, there is Sabatov's algorithm.
Okay.
As far as I know, that's the only.
That describes the edges of the polyhedron.
No, you get the dihedral angles out of Sabatov's algorithm.
No, where the edges are. I mean,
Oh, where the edges are. That's not as difficult because they must be shortest paths between the vertices. You can find the vertices. You draw all shortest paths between all vertices, and amongst them are the edges, and you could try all possibilities. Again, completely impractical. But in general, no, we don't know how to find the creases in any practical way. The way that if you build it out of paper, the polyhedron forms in your hand, which is an indication that you should be able to solve this.
Okay, you finished. Okay.